Log on, tune in, find out. Another good idea from Cambridge.
Sorry about that. So my name is Jan van Leeuwen, University of Reading, and I'd like to talk about particle filters. And to some extent, this is not really an inverse problem, but I think it's interesting to see what happens here. So first of all, the problem I'm working on is typically really large-scale problems in general the geosciences. As an example, numerical weather prediction, state size some 100 million variables, observation vector of the size 10 million, that kind of problem. So I'm not working on parameter estimation, at least not yet. I'm working on state estimation, so variables that change over time. So we do it for the atmosphere, for the ocean, and etc. And all have in common a set of nonlinear PDEs coupled to each other, and they describe the evolution of the system, and the observations are sparse in time and in space. So that's the problem, I didn't specify the problem. So the problem that I want to do is to infer something about state vector. Now, from the field where I come from, we call this problem data assimilation. The idea is that you have a system and you assimilate data when you move the system forward in time. So my starting point is a model and a PDF of the model. So that's a probability density of the state vector, and it's given by my model. And then I propagate this thing forward in time in some way, and then at some point I get observations and I can construct the likelihood. So I know the error structures of my observations. I assume they're known, and then I can get this likelihood, and then I have to combine these two PDFs, and we get this posterior PDF. Now we know how to do this, Bayes' theorem. So just, as you see here, we're interested, the solution to my problem would be this posterior PDF. So the solution is a PDF. And here you can see by notation, by the way. So X is the state vector, the thing I want to know about, and Y are my observations. And what you see is it's just a multiplication of the prior and the likelihood. And so the solution is a PDF, and you see there's no inversion here. So the denominator here is just a normalization vector. The data simulation problem is just a multiplication problem. And so the philosophy is a bit different from typically what I tend to hear here in this room from other speakers, where they say, I have a set of observations and I want to infer something from the observations, and then then I have an underdetermined problem and it's ill-posed and whatever, and I have to come up with regularization terms to solve this problem. And here we start from a different point of view. We say, well, actually, we know quite a lot about the system. So that's our starting point, or present knowledge, and then we're going to incorporate the observations, etc. And then you see, as soon as you have that, you work with that set of mind, then we don't have an inverse problem, we have a multiplication problem. Now, what I heard a lot about is that we try to, if you look at what you're doing, the equivalent would be to find the mode of this PDF. This is typically considered to be the best solution. And now let's have a look at this mode. But before we do that, also when you do parameter estimation, there's no inversion involved, right? I have prior knowledge of the values of my parameters, and they are put in the prior, and I just multiply the prior with the likelihood, and I get my posterior PDF. So, and of course this function h here that connects parameters to observation can be very complex, but it doesn't make it an inverse problem. It's still a multiplication problem. Okay. Now there are several reasons why I'm not too happy with the mode of the posterior PDF as a solution to the problem. But I must confess that in the atmospheric community, numerical weather prediction, that's what they do. They look for the mode of this posterior PDF. It is in a method called 4D VAR, four-dimensional variational method to solve that using conjugate gradient methods, etc. And but also these guys start to realize that there's a lot of problem, right? Because the size of the system, the number of independent observations, nonlinear observation operators, etc., the nonlinearity of the model, a lot of local minima around, and of course they realized they have to come up with a good uncertainty estimates. So you want to know how good your system is. Those of you who were here yesterday might remember that I did ask a few questions along those lines. What is the uncertainty estimate of your solution? And and the last point I'd like to elaborate a bit on: how relevant is the mode probabilistically if you are working in a very high dimensional system as we are. So let's have a look. Let's take this simple. I guess that the majority of you actually know this, but perhaps not thought about it in this way. So if you look at the Gaussian PDF in high dimensions, and let us assume, just for simplicity, that all the variables are identically independently distributed, well, according to this Gauss. So this is my PDF. I'm not talking about data simulation, just in general, we have this PDF, and the question is, what does the mode mean? Now, of course, along each axis, it looks like a standard, this is just a standard Gaussian, and nothing strange about it. But if we start thinking about these high dimensions, and we think about where is the probability mass, so where is the mass in the probability mass of this Gaussian? And of course, we know that the probability density peaks in the center, in the middle, at 0. But where is the probability mass? And then, so what we can do, for instance, we can look at the probability mass as function of the the distance to the center, the distance to the origin, r. And if you just do that calculation, this thing over here, then, then you get this kind of dependence on r, and you have here the integral of all the angles in the high dimensional space. And well, when you just look at what this function looks like, so this probability density, what does it look like as function of r in units of standard deviation, then we see that when the dimension of the system is 100, then this thing really peaks at r is 10, and the probability mass close to 0 or whatever or elsewhere is just well 0. All the probability is located at about 10 standard deviations away from the mean, from the center. And if we go to a 400 dimensional system, we go to 20, and 900 dimensional system, we see that we're just moving away at getting a larger distance from the center. So that's why people call this an importance ring around the center. So that's where the probability mass is. Now, if we continue along these lines, one of the questions is why is this happening? Well, the thing is that if you look at the volume of a unit sphere, then in high dimensional system it goes to 0 quite rapidly. And it's easy to sort of get some feeling of it. So if you look at the one-dimensional system, and I have this unit, I take a unit cube. Of course, a unit cube has a volume 1 in all dimensions. And now compare the cube to a sphere, the unit sphere. Now, one dimension, the unit cube, and the sphere with the radius 1/2 doesn't really matter. It's 1 or 1/2. You see that they're of equal size, right? So they have the same volume in 1D. If you go to 2D, we see, of course, that the sphere doesn't cover all the area. You see the 4 areas over here that that reduce the volume of the sphere in 2 dimensions. Now, you can imagine if you go to higher and higher dimensions, these areas become relatively larger and larger. And actually, they dominate, and you see that the volume element goes as 1 over the factorial of the dimension of the system. So that goes pretty fast. So that's the reason why the center of this, the PDF, it's just, there's no probability mass there. It's actually, probability-wise, not an important thing. Yeah. And so if you would think about, I have this posterior PDF, and I'm going to draw, let's say, 1 million samples from that, and then the mode, the mean, is never drawn. There's no probability mass in the center, especially if you go to, well, like I said, high dimensional system, 100 million dimensional systems. So that's about the mode. Now think again about this nonlinear data simulation problem. How do we solve it? What I don't know, but this might be something useful, the particle filter. Now, some of you have undoubtedly heard about the particle filter. I'm going to talk about some special flavors of it that make it useful for these high dimensional systems. So I've written down Bayes' theorem again, And the idea of the particle filter is just very simple. Well, you just take samples from the prior, and so you can write the prior as the sum of delta functions over here, and xi is the index I is the sample index, and then what you do, you plug this equation into that one, and you get, for the posterior PDF, you get this expression over here. Again, the posterior PDF now is again a sum of delta functions, but they are now, it's now a weighted sum. So here the weights are all 1 over n, all the same for each sample, and here they become weighted, and the weights are related to the likelihoods. And that's all. That's what data simulation is in such a system, and or in the particle filter. And so what are these weights? Well, so they are blah 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 blah. So typically, if we assume that the errors in the observation are Gaussian distributed, and these errors are correlated with an error covariance big R over there, then these weights would be given by this thing, and this expression over here, just the Gaussian. Of course, I know the value of the observations, I know my samples. I can just calculate this expression for each sample, and that's what it is. And then, when I've done this, then I've solved the full nonlinear data simulation problem. I have an expression for the posterior PDF in terms of weighted samples. That's all there is to it. Now, unfortunately, that doesn't work, and I'll show you why when the size of the system is large. Well, actually, I should say when the number of independent observations is large. So suppose I have a prior PDF given like this. Could be anything. Let's assume it's this. Now I just in some way generate samples from them, and these are my samples, and the size of this bar is just the weight of each of these particles in the PDF. Now what I'm going to do, like I said in my problems, we have this evolution of the system to the next set of observations, and then I'm going to do the data simulation there. So let's evolve this set of particles forward in time with my nonlinear model equations. So what I'm doing here with these samples, I'm trying to solve the Fokker-Planck equation, if you like, right? I'm trying to solve the evolution of the PDF with just a number of samples. So this is the new time. I have here are my samples, still equally weighted, and then I look at my observations. So assume this is my likelihood. So the observation is somewhere here, and there's some spread around it, the errors in the observation. And now Bayes' theorem told us no inversion, multiplication. So I'm going to multiply this green function with these blue bars, and then of course this is what I get. And well, this is not very efficient, is it? In the sense that what has happened to the particles over here? Well, particles or samples, it's the same thing. You see that the weight of all these particles have changed. The ones that were in this area had a very high weight now, and the ones over here were weight, well, almost 0. So if I would calculate, let's say, a mean, that would then be the weighted mean. And so for the weighted mean, I would only use, well, in this case, 4 particles to calculate the weighted mean. That's that will be a poor estimate of the mean, right? So you see, this whole procedure is not very efficient, and that's the reason why particle filters, well, have a pretty bad name in these large dimensional systems. And but we can improve on that, and I don't want to talk about this. So how does it work? So first of all, we should realize why is this so bad? What is going wrong with these particle filters? And why is it not just the dimension of the system that kills this idea? Well, the thing is that this is sort of known as the curse of dimensionality, but it's again, it has to do with the observation. So let's suppose this is my high dimensional system, and I have one observation of one of the variables of my system. So this is let's say 100-dimensional space, and I have one observation of one of the variables, which means that I want to restrict. Well, now let's put it this way: the particles will have a high weight when they fall into this hyperplane related to that observation. Of course, the hyperplane has a certain thickness related to the error of the observation, but that's where the particles should end up. Will they have any a reasonable weight, a non-zero weight? Now this is one observation. If I add another observation, you see it's actually they have to end up in the cross section of these two hyperplanes. And if I continue doing that, then you see the more and more observations I add to this problem, independent observations, the smaller and smaller the area in state space becomes where I have to, where the high weight particles will be, where the high weights will be if I manage to get my particles there. So now you immediately understand why the standard particle filter is just not a very smart thing. Because what you do, I'm standing here, so this is time, I'm standing here, and I will have observations over there. So what I'm doing, so each of these particles, I just shoot them blindly into space. So one of them will go over here, and someone will whatever, and so they go everywhere. And of course, you want to move the particles, make the particles smarter. You want to, if you like, let them know where they should go, and you can actually do that in the particle filter. And again, this is not a new idea. Proposal density is not new. It just has to do with importance sampling. So it's actually slightly different from what I'm presenting here, but just in the interest of time, I'm doing it this way, and this does have the fundamental ideas. So this is again Bayes' theorem, written slightly, the denominator written differently, but it doesn't matter. So what I'm going to do, I take this equation here, I just multiply by q of x, there's another PDF, and divide by q of x, and I can always do that. And as long as q is not 0 where p is 0. So what am I saying? Well, anyway, so q should not be, let's say q should not be 0. Yeah, but p is non-zero. That's what I wanted to say. Now the thing is, so what I can do now, instead of drawing my particles or my samples from p, I can now draw them from q. And I didn't put it here in the notation. I should have done. This q, they can depend. This q of x can actually depend on the future observations. And so what I do, I draw my particles, and these particles are already informed about the observation. So instead of starting my random walk into state space and hope I end up close to the observations, I first wait until the observations are there, and then I start walking, looking, knowing where the observations are, so making sure I end up in the right places, area of state space. So it's the same thing. So again, I have the sum of delta functions, and the posteriors will again be a weighted sum. And if you look at the weights, it becomes slightly different. We have these weights are now related to the likelihood, but I've made sure that the particles all end up close to the observation. So this part of the weights will be relatively uniform, and then this part, which is this p over q, the prior divided by the proposal density, and this term actually gives more spread to the weight, but I can looking at this whole term, I can make sure that all the weights are relatively are similar, pretty close to each other. And so just the idea, I just want to sketch the idea. Again, I have a prior PDF here, and here are my particles. And now, instead of starting the integration of the nonlinear models, I wait until I know what the observations are in the future, and only then I'm going to run my particles. And at each time, I mean, there are several ways to do this, but what you for instance can do, you can just add a relaxation term towards the future observation in each of the model equations to force each particle towards the observation, so that all of them end up close to the observation. And of course, you're cheating then, because you're changing your model equation. You're solving a different problem, you might say. Well, that's actually not true, because, like I said, at the same time, we have this extra factor in the weights, and that compensates statistically for the change in the model equation. So you can just do that, and you solve. If you could do an infinite number of particles, you would solve the complete nonlinear data simulation problem. Okay, so here are my particles. You see much more efficient and much higher weights, etc. Much more uniform weights. That's actually what I wanted to say. Now let's have a look at this example. So I applied this methodology. There's actually a bit more to it, but anyway, let's just give you a flavor of the kind of problems we're working on. So this is the kind of problem I want to do the data simulation on. So this, so what you see, the red and the blue these are vortices, one rotating in one direction, the other in the other direction, and you see the interaction of these vortices, and you also see, well, this sort of, if you like, resembles, well, maybe the atmosphere or the ocean, whatever. Now this is a high-dimensional problem. In total, some 65,000 grid points. I observe this system every 4th grid point, every 50th time step, and I know you're perhaps not familiar with these time-dependent problems, but I probably should say that the decorrelation timescale of this system is about 25 time steps, and I'm observing every 50 time step, which means that the information I put in from the observation at one time step is quickly lost in the system. It's actually typically sort of lost before I do the next data assimilation step. So this is really a very hard problem. Now, what I'm going to do if you want to do the standard particle filter on this, you would need trillions of particles, right? Which is sort of undoable. We're going to do this with 24 particles, so 24 model integrations, and see what happens. Now, give you an example. So here we have the truth. This is the evolution of the truth field, and this is what this standard particle filter would do. This is the mean of all these particles, and you see these changes. So it evolves of some time, then you get this change, and that's when the observations are included in the system. And you see this is terrible, right? So the standard particle filter, 24 particles, just doesn't work as expected. Now this is the new method. So again, the truth evolution of the truth field over there. This is the mean of the ensemble over here, and you see we more or less trace what's going on. Of course, we only have observations when we have observations. I see that it's interesting. I get something different here than on the screen, but I understand I'm not the only one. This is actually, I think it actually mixed up the two. Well, I'm not entirely sure what happened here. So, well, you should come. This is really strange, actually. I'll give it another try. It looks as if it was mixed up the system. Well, anyway, no, it doesn't. Well, it's very sad. I'm sorry. It should look really much better. This is the one. Well, I don't know what it's doing. This is really strange. I don't know. I'm sorry about that. Anyway, so what we should have seen, but I don't know what is happening, is that the end result of the mean of the particle filter is very, very close to the truth. And I don't know. I don't know what has happened. I'm sorry about that. So the idea was to show that that this new method worked really well. But it's a bit frustrating. Anyway, just to show you some statistics. So here are the weights of the particles. So their weights, and you see that they tend to cluster about 1/20, which is what you would hope that they do. Right? The weights are more or less equal. There's some small scatter, and there are about 5 particles over here that have weight, a much smaller weight, and they're not a problem. They come into the problem again with resampling. So we know what's going on there, and it's okay. We don't have to worry about it. Anyway, another way to look. Of course, one of the problems is for these high-dimensional systems, we don't know what the true posterior PDF looks like. We have no idea. It can be anything. And to know that, well, the only thing I can think of, you have to do some. Either use 1 trillion particles in the particle filter, or use some smart hybrid Monte Carlo method or whatever to try and figure out what the shape of this posterior PDF is. It's a problem. It's a real problem. So what I did here, but of course you can look at the consistency of the internal statistics. So what I've done here, I've binned my particles here for one of the variables, smallest value and all the way to the largest value, and I looked where the truth is in this binning. So if the true value is smaller than all the particles, it ends up in the first bin. If it's larger than all of the particles, then it ends up there. And if it's, let's say, between the value of particle 10 and 11, then it ends up in bin 11. So And I just run the data simulation experiment a very long time and just gather statistics. Now, if it would do well, then this thing would be distributed uniformly, which would mean that the truth is indistinguishable from any of my particles. So any of my particles, so any of my evolutions of the system could be the truth one. The truth is just indistinguishable from that. Now you see, it's not really uniform, but it's close to uniform. And if you are familiar with this kind of plots in this kind of settings, then you would agree with me that this is actually pretty good. Of course, I can do a statistical estimate how good this is, but I don't think that's worth the effort. So anyway, to conclude here, the first point is that the posterior mode might not be the most relevant thing in these high-dimensional systems. And the second thing is that particle filters with the proposal transition density, well, I didn't really show it, I realize that, but they're doing a very good job. But I must confess that I'm trying to represent this high-dimensional PDF with 24 particles. What am I doing? What actually do they represent? I can calculate the mean, I guess, or some error estimate, covariance, whatever, but well, it's still a bit unclear what we're doing here. But at least in the limit of an infinite number of particles, we are solving the correct problem. And that's all I have. Thank you very much.
Time for one or two questions. Please.
There's two questions in the back.
Henning.
You said that in your proposal, forward proposal, your Q, in this, that you added, when you proposed, you knew something about your likelihood. But how do you, is that a simplified model of a differential equation, or is it linearization?
No.
I mean, it must be linked to your forward model in one way.
It is the full forward model, because all that physical knowledge is there. I want to use it, so it's the full forward model. But the simplest thing what we did is we added a relaxation term towards his future observation.
So you shot out a little bit too wide. That's some sort of what you said in the proposals.
Well, typically you don't know where to go to, right? So typically you shoot it too wide, indeed, and then but now we force it towards the observation. And there are more. I mean, you can solve an inverse problem for each particle, if you like, if you want to call it an inverse problem, and do it that way. To get in that way the future. Well,
but it has to be linked to your physical model, obviously.
Well, I think that would be the best thing to do. Yeah.
You mentioned that you didn't use the standard particle filter, but like a better particle filter.
Yes.
And I guess that, using importance distributions is standard. So what was the, how was it different from standard?
Well, the thing is that we, I agree with you. This proposed density idea, that's, you can also say, well, that's the standard particle filter. What would I do? I guess, well, that's related to the last one. So the thing is, when you just do the relaxation, then you look at the weights are still all over the place. There are a few particles with high weights, and most of them have weight very close to zero. So what you can do, however, so I use this relaxation scheme up to the last time step, and in the last time step, I calculate an analytical expression of the weights, and then as a function of where the particle, the potential future position of the particle, and then I make sure that all the I'm going to choose the position of that particle such that I choose a target weight for all of the particles, and then I'm going to choose the motion of the particle. So my proposal density, the last time step, is actually determined by what will the weight of the particle be. I want the weight of the particles to be, well, whatever, 1 over 20, and make sure the weight will be 1 over 20, and then I'm going to figure out what the move of the particle is. And that's of course a deterministic step, so I have to add a random step to that, and well, I can do that. So that's the trick. You use the proposal density in a special way, not only looking at the observation, but saying, no, I want the weight of the particle to be exactly this. And you can do this. You have that freedom, and that's what we exploit. And that's a new ingredient.
Maybe we should take a break and we'll resume at 3:30.